Hello, everyone. This is Mr. Arrington, of course. There were a couple of things that I wanted to cover before we were prematurely interrupted. And so I wanted to take advantage of this time and cover, the concepts I was trying to get to prior to our departure. Good news is the other day on a link that I sent you yesterday, they kind of covered kind of the preface, if you will, for these exponential growth differential equations that I would like to cover. I thought today that they may have covered the things I'm about to cover, but they really did not. They kind of took a total different turn. So I guess that's good. It allows me to kind of attack what I needed to cover. So hopefully most of you watch the YouTube video from the College Board on Wednesday, yesterday, because again, it kind of gave the framework for what I'm about to do. If you didn't watch it, it's probably a good idea to watch that first. I'll try to put a link in the description of the link to that, which I've sent out numerous occasions on emails. Probably a good idea to watch that first. It will make what I'm about to cover a little more digestible. But anyway, so what we're dealing with, and I just noticed a typo here, what we're dealing with is exponential growth differential equations. That's exponential growth. Exponential growth differential equations. And so a lot of you guys probably been watching the news about this virus that's overtaken the world. And you've probably heard many people coming up talking about models for the projections of how many people are going to be infected and die, and et cetera. The models for cases like these, the models are actually simulated with exponential growth differential equations. So you're about to kind of see the math that goes behind that curve that they always refer to. And you'll also hear them talking about how many days the number of cases doubles. So finding that doubling number is something that we do in these type of differential equations. So I guess in a sense, it's kind of good to see something that they talk about almost every day on the news kind of applies to this. So let me describe, or rather define, what an exponential growth differential equation is. And we say exponential growth. Technically, it can be exponential growth or decay. So when we say exponential growth, implicit in that statement is that it could also refer to exponential decay. You learn about exponential growth and decay in Algebra 2. And so this gets a little more complicated than the presentation I was presenting in Algebra 2, but it's kind of the same thing. So let me give you a verbal description of what an exponential growth differential equation is, and then I'll write the equation. It's a very simple equation. So an exponential growth differential equation is a situation where the rate of change of an amount is directly proportional to the amount. So I'm going to state it again. So an exponential growth differential equation is a situation where the rate of change of a certain amount, generally in real life, it's like a population of bacteria, population of people, but the rate of change of the population or the rate of change of an amount is directly proportional to the amount. The equation looks like this. So there you have the basic exponential growth differential equation. As you can see, what I have written is dy by dt, so that's the rate of change of y with respect to time, equals ky. And if I'm saying that equals ky, that means it's directly proportional to y. And that part, that understanding of that, that's kind of what they covered on Wednesday on the YouTube deal with the College Board. This guy K is called the proportionality constant, and it's also just called the growth factor. So K is referred to as the proportionality constant, or just the growth factor. Now, if you look very clearly at this differential equation, because we're going to solve it, its solution is very important to us. Its solution is one that you would like to remember. Look very closely. K is just some constant, so K is not a variable. Our variables are y and t. If you look very closely, this is a very simple, separable first order differential equation. It's a very simple, separable first order differential equation. So I would like to solve it because, again, the solution is very important to us. So I'm going to separate this guy. Now, of course, if you look at the differential equation, what I need to do is I need to move y over to the left to join dy. And of course, the y will go to the bottom, and I just move the dt over. So the separation is going to look like this. So there it is. I have successfully separated. And after we separate, we integrate. So now I begin to very carefully integrate this guy. So you see me integrating. I'm doing it right before your very eyes. And so everybody knows that the integral of dy over y is, of course, what? Correct. Ln y. And now remember, k is some constant. The right-hand side is being integrated with respect to the variable t. So the integral of k with respect to t is just kt plus some constant. So I haven't solved it yet. I've integrated, but I haven't solved it. Solving a differential equation is finding a y equals expression. So, of course, if y is the dependent variable, of course, it could be other variables, but in this case, I need to put this in y equals form. So in order to put it to y equals form, this is something you should be very familiar with. I'm going to make everything you see there, I'm going to make it exponents of e. And how we say that in the business is we're going to e this junk. So let's e this junk, shall we? So if I e this stuff, I have e to the power of ln y equals e to the power of kt plus c. Now, of course, e to the power of ln y is, right, y. Now, e to the power of kt plus c, based on the properties of exponents, is e to the power of kt times e to the power of c. So e is a constant, c is a constant. So e raised to the power of some constant is just some constant. So e to the power of c is just a constant. So e to the power of c is just c to me. And so I'm going to rewrite this, and this is the final finished product, ready to go out on the shelves. The final finished product, articulated before I write it, will be y equals c times e to the power of kt. That's it. That's the magic. That's the moment we've been wanting. So let me write it now. So the solution to the differential equation is y equals c times e to the power of kt. That's a very famous solution. That's a solution you want to remember. Now, if you look very closely, to solve the differential equation that we had, dy dt equals ky, it's pretty simple to solve. Most of us can solve it in our sleep. in general, when things are very simple to do, we don't really want to memorize the solution because we can find the solution in a matter of seconds. However, this is a very unique case where this is a very popular solution of a very well-used differential equation. And so it would be very advantageous to memorize this solution. So therefore, anytime you see the differential equation dy by dt equals ky, which we called an exponential growth differential equation, you already know its solution is y equals c times e to the power of kt. Now, you may have noticed that I wrote my c as a capital C. And you may say, well, why didn't you write your c as a lowercase c? It really doesn't matter. I could have wrote it as a lowercase c. I could have used a letter other than c. I could have used any other letter in the alphabet. I could have used a Greek letter. Just typically, and normally the letter that's used for this is capital C. Now the C is important. So in this solution, we have y, which is a variable. We have c, which is a constant. We have e, of course, which is a well-known constant. We have k, which is a constant, the proportionality constant. And we have t, which is a variable. So we have two variables, y and t. We have two constants that typically we need to find, c and k. We don't need to find e. E is a well-established constant. So I want to dig a little deeper and get a full understanding of what c represents. So again, we say k is the proportionality constant or the growth factor. But let's deal with what c represents. So let's say we had an initial condition to the given differential equation. And again, what you see boxed on the screen now is the solution to the differential equation. And again, just the differential equation that this was a solution to was dy dt equals ky. So the solution to that differential equation is the guy you see boxed. But let's say we had this differential equation and we had some initial condition where y of 0, so that's the value of y when t is 0. So this is the initial value. So what I'm writing is the initial value of this. In fact, so let me state it as so. So I have this, let me rewrite the solution. So the solution is y equals c times e to the power of kt. That's the solution to my exponential growth differential equation. And let's say I have this initial condition that y of 0. Now again, y of 0 is the value when t is 0. So that's the initial value. So that's actually what I'm going to write. So y of 0 equals initial value. Now, in your textbook, and I'll look at your textbook and tell you what chapter this is in. In your textbook, this is called an initial value. In many books, for instance, this is one of my many, there's no need to get it. In many of my differential equations books, this is typically called an initial population, because these exponential growth differential equations are normally used for measuring of populations, whether it's a population of bacteria or a population of human beings. All right, so now again, in this initial condition, y of 0, this 0 corresponds to t, and this guy over here corresponds to y. So in the solution, I'm going to plug in 0 for t, and I'm going to plug in initial value for y, and then I should be able to solve for c. So I want to show you exactly what c represents. All right, so let's plug it in. So I'm dealing with this guy here, and I'm going to turn this y, you see, I'm going to turn this y into initial value, and I'm going to turn this t into 0. So let's see what happens. So let me just rewrite this. So y equals c times e to the power of kt. And I'm going to plug in initial value for y. So this y becomes initial value c, e, k, and t becomes 0. Pardon my 0. That's definitely a 0. It, actually, it looks too bad. Leave it like that. So let's try that guy again. Bam. That's what the parenthesis there took a hit. And the 0 got a little excited on the beauty of the 0 and then messed up on the ending of the parenthesis. Okay, there we go. So k times 0, of course, is 0. Yes. E to the power of 0, of course, is 1. Yes. So, and c times 1, of course, is c. So what ends up happening is c equals the initial value. So in this solution up here, again, I have two variables, y and t. They vary. They're going to vary, depending on what's going on. I have three constants. One constant that, is a well-established constant. So I know what it is. That's E. So E is firmly established. There are two other constants, C and K. K we already talked about is the growth factor or the proportionality constant. And C actually is the initial value. That's very important to remember. That C represents the initial value of the situation. All right. I want to give you an example of a problem. So I had some right here. I actually have the problem memorized in my brain computer, but I would rather show you the example here. So because if I write it, writing might be a little bit on the sloppy end. Let's see. I think I'll go and write it. So this is an example of a problem you would have to solve. So it says if dy by dt is 7y, so dy by dt is 7y, and y equals 13 when t is 0, y equals 13 when t is 0. And then it says then y equals whatever. So find y. All right, by y, it wants you to find the actual equation of y, not some numerical value, the actual equation of y. So if you look very closely, and so you're going to have to be able to recognize this when you see it, they're not going to always say, well, they're never going to say, hey guy, you're looking at an exponential growth differential equation, solve them. So you have to be able to tell by the look at it. So when I see this, and I see its form, I have a derivative, I have dy by dt, and the dependent variable is y. I see on the other side, on the right-hand side of the equal, it's just a constant times that y. Whenever you see that, you're looking at an exponential growth differential equation. So your job is to find this. So they want you to find y. Well, when you know the recognition, that's why it's very important to remember solution. Y is c times e to the power of kt. Here's y. I found it. However, I need to find it and I need to plug in the values of c and k. I don't need to plug in y. Y is a variable. It will vary. I don't need to plug in the value of t. T is a variable. It will vary. And so you can think of y like the number of cases of COVID-19 in the US. You know, when T was whatever 3 days were ago, I think the number was around 800. Today, this Y value is around 80,000. So the Y and the T, those guys are going to vary, so they're going to stay Y and T. However, the proportionality constant will remain the same unless the model requires us to find a new function to simulate it, and that of course can happen in real life. And the initial value, which is C, is going to remain the same. So to solve this problem, I just need to find C and K. Now, if you think about it, C and K are looking you dead in your face. So let's go back to the given problem. The given problem is dy by dt equals 7y, correct? Okay, well, the general form of this type of differential equation is dy by dt equals ky. So guess what the value of k is? Yes, you guessed it, 7. K is 7. So I found k. I need to find c. C is the initial condition, the initial value, the initial population. C is the value of whatever y represents when t is 0. Well, look, when t is 0, y is 13. So C is 13. So then what does y equal? Y equals 13e to the power of 7t. K was 7, correct? I forgot the problem already. Yeah, K was 7. So y equals 13e to the power of 7t. Problem solved. Now, that was a pretty vanilla type of scenario that you'll see with these problems. These problems can get a little worse than vanilla, particularly when you're finding the time it takes for a population to double and things like this. These are a little more intricate problems. And the doubling type of problems are not a case I would like to get to today, but I would like to look at one more type of example for you today. Which chair is kind of squeaking a little bit. That may be somewhat of a disruption to the learning process. So I'm looking for something that's along the lines of what I'm looking at right now is a list of problems I've created. I'm looking for something that's pretty good, but it's not a bunch to write. I'm writing these problems on an iPad. It's limited space. It's a fairly difficult deal to do. I'm going to go ahead. I'm going to go ahead and do a problem that I wasn't really trying to do today. But of all my problems I'm looking at, it's like the shortest problem. So it's actually a doubling problem, I believe. Well, actually, it's a quadrupling problem. So it's somewhat of a technical problem, but it doesn't have a lot to write. So I'm gonna go ahead and do it. So it's gonna require a calculator. And so I'm gonna bring out a calculator to do this problem. And I'm gonna show you guys have a couple, those of you that don't have calculators, you have a couple of ways to access an online calculator for free during this time, and I'll mention that after this example. So the problem says population Y grows according to the equation dy by dt equals ky. So nothing overly creative about that. So again, all it says is population y grows according to the equation dy by dt equals ky. So it's saying, hey guy, hey girl, this is an exponential growth differential equation going on. And then it says where k is a constant and t is measured in years. And then it says if the population quadruples every 2 years, so population quadruples, pardon my handwriting, quadruples every 2 years, I believe. And t is measured in years. So the population quadruples every 2 years, then the value of k is what? So find k. All right, so this is a good problem. So we're gonna find k. And so I talked about doubling. And so when I made these problems, I made some quadrupling, some tripling, some doubling. But mainly what's measured is the doubling. But quadrupling is, it's done the same way. It's just not called upon as much as a doubling problem. So I want to find the value of k, correct? All right, so every 2 years, the population quadruples. So let's look at this. So the population is y. dy by dt is the rate in which the population is growing. So the population is y. So I'm going to solve this differential equation right here. You already know its solution. Its solution is y equals c times e to the power of kt. So I'm going to write that solution. All right. And so at t equals 0, this guy equals c. Would you agree? So at t equals 0, c, y would equal c. So at t equals 0, y equals c. So y of 0 equals c. Everybody would agree, correct? C is the initial condition, it's initial value when t equals 0. Now, so at time t equals 0, y equals c. Every 2 years, however, it quadruples. So at y equals 2, this should equal 4c, correct? At y equals 2, this should equal 4c. So here I have a value for t. I have a value for y. I'll plug those values for t and y into this solution, and then I'm going to solve for k. So solve for k is I'm going to do a little ln deal to solve for k. So that's why I'm going to need a calculator, but that's what I'm going to do. So I'm going to turn y into 4c, and I'm going to turn t into 2, and then I'm going to solve for k. All right, so let's see how it looks. So y becomes 4c. So 4c equals c times e to the power of kt. Well, t is 2. So e to the power of 2k. Now you may notice that you have a c on the left and the right. So we can divide both sides by c. So 4 equals e to the power of 2k. Now, to solve for k, I want to ln both sides of the equation, correct? Because k is up here as an exponent of e. So to get it out of an exponent of e, we ln it. Just as to get rid of ln, we e. So these are things you're familiar with. So I'm going to ln both sides, and I'll get ln 4 equals ln e to the power of 2k. But of course, ln e to the power of 2k is just 2k. So ln 4 equals 2k. Now, this is something you want to remember. So this is for any problem. And so let me write this bottom expression on a fresh new page to point out a couple of things. So ln 4 equals 2k. ln 4 equals 2k. Now the 2 you see in front of k, this is when it's a doubling problem, it's called the doubling time. Of course, this was a quadruple problem, so we call it the quadrupling time. I ran out of space, you know, in front of right, so I'm writing quadrupling time. So, for instance, if it said the numbers quadruple every 7 years, there will be a 7 there in front of k. Every 8 years, there'll be 8 there in front of k. Now, this number for the ln, this is what the population is doing. So since the population was quadrupling, I have ln 4. What population is doing? So if the population was tripling, it would be ln 3. And for those very famous population doubling questions, of course, it's going to be ln 2. So this is a very common type of question that's asked. So if the population is quadrupling every 2 years, what's the value of k? So if you understand the setup from that statement, you can go straight to this, to solve for k, straight to this. For instance, you know, if they said if the population was doubling every 10 years, then right then, and they say what's the value of k, then right then I know to write that ln 2 equals 10k, and then easily solve for k. So you can see right here what we have set up is a very easy thing to solve for k. So I call upon you to memorize this equation here. Whenever they ask you to find the value of k, when they talk about a population doubling, tripling, quadrupling, or maybe getting 7 times bigger, whatever, in a certain number of time, you can go to this guy to easily solve for k. So let's solve for k, shall we? So we have ln 4 equals 2k, and so k, of course, is ln 4 divided by 2. That, of course, is not equal to ln 2. It's ln 4 divided by 2. So let me get a calculator. I can apologize for the chair. Maybe perhaps a little oil is needed for this guy. So ln 4 divided by 2 is about 0.693. So k is 0.693. All right, so what I'm going to do is today I discussed 2 types of exponential growth differential equations and went over a couple examples with you. What I'm going to do is I'm going to put up a connect ed assignment over these type of problems and see if you can do them. Of course, this solving for k problem, because it's always going to be ln something divided by something, and you're going to need a calculator. So I would like to point out you a couple of places you can find calculators. For just doing regular stuff like this, just ln something divided by something, Desmos has a calculator. You can go to desmos.com/ well, when it comes up, it's going to give you an option of for function or a scientific. So Desmos.com, that's pretty sloppy. I had all this time to be working on my handwriting, and you guys deserve a little bit better than that. So I'm gonna rewrite this. So Desmos, I actually should have typed it. Desmos.com. Actually, that's one of my best ideas I've had. Let's type this, shall we? So a website you can go to would be desmos.com/scientific. Looks like I spelled everything correctly. So that's where you can get just a basic calculator to do calculations like we just did. TI has got a special thing out where you can get the graphing calculator. The graphing calculator we normally use. There's a link they had where you can download that on your computer. I'm not sure if that downloads on the phone. I know WabbitMU you can use on Android. I'm not sure if this TI downloads on the phone, but it can definitely download on the computer or an iPad. I'll send an email with the link. It's somewhat of a long link, and you can use that for a graphing calculator. I have yet to understand what's going to be the calculator deal for the AP exam. They're coming up with further details on April the 3rd. So April the 3rd, I guess we'll know. Now, hopefully you've heard, I've tried to say this in an email, that this year's test is condensed. It's only going to be 45 minutes, and it's only going to be free response. So there's going to be no multiple choice on this exam. And this is all exams, actually, all AP exams this year. They're all going to be just whatever their free response is. And so again, there'll be more details on that coming out on April the 3rd. I would assume they would be calculator problems, but maybe not. But if there were calculator problems, I guess they would give you some type of calculator used. And since it's 45 minutes, they haven't, again, they'll come up with further details on April the 3rd, but the typical rate is 15 minutes per free response problem. So it's looking like you're only going to have 3 problems. Again, as they're going to release specifically what is going to be over on April the 3rd, and when they release that, we'll be able to attack it and be very well prepared for it. So I know some of you don't like free response. Well, most people don't like free response, but we'll have plenty of time and we'll know exactly what is over, that we can prepare where everybody can be successful. So it's been a pleasure speaking with you guys. I'm going to drop a few more of these. I'm going to drop several of these videos as time progresses. I've had some technical difficulties doing this, so I actually tried to do this yesterday, and there were some issues, and so those issues may cause delay on some things. But again, it was great to greet you guys. I also plan to do later. I'm recording this on Zoom, so I'm going to try to do some Zoom tutorial sessions a little bit later, so you guys can ask me questions face to face and stuff like that. I will look at doing those type of things next week, and I can try to answer whatever questions you have on the AP classroom assignment. But once again, it's been a pleasure. I hope you guys are making the best of this situation. Whatever life presents to us, we try to just make the best deal we can of it. And once again, it's been a pleasure being your teacher this year. Any questions on this, you can always contact me via email. I'm always here to help. Again, you guys have a great day, great year, and we'll see you later. I'm out.